Welcome to iLecture Online, and here's a short lecture on how the microscope works and how to find the magnification of a microscope. Now, that's a little bit more complicated than it is for a telescope, but hang in there and follow it very carefully, and I think we'll be able to explain this to you. Well, just like a telescope, a microscope has two lenses. The one in the front is called the objective lens, the one in the back is called the eyepiece. Unlike for a telescope, both focal lengths of both lenses tend to be very short for a microscope. And let's say that we have an objective lens with a focal length of 5 centimeters in the front, and we have an eyepiece with a focal length of 2 centimeters in the back. The observer is looking through the eyepiece. The way you set this up is you place the lenses far enough apart so that there's a lot of distance between the two focal points of the two lenses. And this here would be the length of the microscope, so let's call L the length of the microscope. And let's say that in this case, L is equal to 20 centimeters, just as an example, so we can work with some numbers in just a little bit, make it easier to understand. Let's say we're looking at an object right here. It's, of course, when you're using a microscope, you tend to look at very small objects, so there's a very small object. And you typically put the object just in front of the focal point of the first lens. So as a starting point, we're going to place it right there, such that the S is equal to the focal length of the objective. So we're going to start like that, and then later on we're going to find the actual place where the object needs to be placed. So if we assume that to be true, then we have the ray coming through here parallel to the optical axis. It bends, goes to the focal point on the other side, and forms an image. And again, you want to form the image just inside the focal point of the eyepiece. Then this ray will then will continue through the to the eyepiece, and then when it gets to the eyepiece, it will then, of course, come back and go to the focal point of the eyepiece, and the brain of the observer will see the ray being bent from the image, of course, of the first lens becomes the object of the second lens, and the object of the second lens then becomes a magnified image over here because the brain sees the ray being bent here to the focal point, and the brain says, oh, I know where this ray is coming from. It comes from way back here, and forms a very large inverted image on the same size as the object, which means it's a virtual image. So this is virtual, and this is upside down. Okay, now, how do we find the magnification of this microscope? Well, first of all, we have two lenses. That means the total magnification is simply going to be the product of the magnification of the first lens times the magnification of the second lens. Now, since the second lens acts like a magnifying glass, let's attack that one first. We already know that the magnification of a magnifying glass is equal to 25 centimeters divided by the focal length of the eyepiece. If we use relaxed vision, or the magnification, let's go m sub 2, is equal to 25 over the focal length of the eyepiece, plus 1 if we use strained vision. When we use strained vision, we position the lenses in such a way that the focal point is such a way that the image is placed about 25 centimeters away from the observer. Strained vision. Okay, and in our example, since the focal length is 2 centimeters, we can say that M2 is equal to 25 centimeters over 2 centimeters, which is 12.5. If we use relaxed vision, or the magnification is equal to 25 over 2 plus 1, which is 12.5 plus 1, which is 13.5 for strained vision. Okay, so now we've found the magnification at least of the second lens of the microscope. Now we still have to find the magnification of the first lens of the microscope. And for that one, we use the typical equation used for magnification of a lens. We can say that M1 is equal to minus S prime over S. So where does the image form, and where is the object placed for the first lens? Well, the image is formed just inside the focal point of the second lens. Since the length of the microscope is 20 centimeters and the focal length of the second lens is 2 centimeters, then we can say that it forms just inside what would be 20 minus 2. So in general, we would say that's equal to minus the length of the microscope minus the focal length of the eyepiece. And then we divide that by the position of the object, and like I said before, we're going to take it, we're going to do the easy approximate example first by setting the position of the object equal to the length, the focal length of the objective lens. So we make this equal to f of the objective lens. Now later on we're going to make a little adjustment to that. But that would be the magnification of the first lens, and so we can then say that this would be equal to the magnification of the first lens, which is minus L minus f of the eyepiece divided by the focal length of the objective, and then we multiply it times either this or this, depending upon if we want to use relaxed or strained vision. So for example, now let's use relaxed vision, so it would be 25 over f sub e. And that would be the magnification of the microscope. So let's go ahead and put in some numbers to get kind of a feel for what that is equal to. So this is equal to, and let me move down here, so that would be minus the length of the telescope, which said was 20 centimeters, so that's 20, minus the focal length of the eyepiece, which is 2 centimeters, and divide that by the focal length of the objective, which was 5 centimeters, right there. And so we multiply that times 25 over 2, because we're using relaxed vision. Now, 20 minus 2 is 18, times the minus is minus 18, so that's minus 18 over 5, times 25 over 2. We already know that 25 over 2 is 12 and a half, then we multiply that times 18 over 5. Let's see what we get. So 18 divided by 5 is 3.6, so that's equal to minus 3.6 times 12.5, and so times 12.5, that would be a minus 45. That means the way this microscope is set up, the magnification of the microscope would be minus 45. Of course, minus means that the image is upside down, but it's 45 times larger than the object we're looking at. But that's of course not the entire story, because really what we don't do is we don't put the object right at the focal point. We actually put it a little bit in front of it. So how far in front of it do we put it? Well, for that we use our equation, our lens equation, which says that 1 over f is equal to 1 over s plus 1 over s prime. Now, if we solve that equation for s, we get s is equal to s prime f over s prime minus f. And that's where we have to put the object to get a nice focused image. So s prime, well, we know what that is. That's equal to L minus f sub e. So this is equal to L minus f sub e times the focal length. Now what focal length is this? This is the focal length of the first lens, of course. So we put sub 1 there, and we put sub 1 there, or of the objective. So let's make it objective here so we can keep it straight. All right, we divide that by s prime, which is L minus f sub e, minus the focal length of the objective. And so instead of writing s is equal to the focal length of the objective, we really should write s equal to that and plug this in for f sub o. Now this is getting a little bit messy, so let me use a slightly different color. So instead, what we can say is that the magnification is equal to m1 times m2. So I'm going to, for the time being, actually it might be easier just to recalculate m1. So instead of using this for m1, which is the approximated value, we're going to use the correct distance for the object distance. We're not going to call it equal to the focal length of the objective. We're actually going to call it equal to this and see how that changes the equation. In the numerator, we still have a minus L minus f sub e. And in the denominator, we now have this new value right here. So this is L minus f sub e times f of the objective divided by the L minus f sub e minus f of the objective. And of course, now we have this divided by a fraction, which is the same as this multiplied by its inverse. But before we do that, we can already see that this and this cancels out, so this becomes 1. And now we can say that this is equal to minus 1 divided by f sub o, which is the f sub o here, and then multiply that times this quantity, which now goes to the numerator, which is L minus f sub e minus f sub o. And that then becomes the new magnification of the microscope. So instead of using this, we're going to use this. And notice how that then changes. This becomes minus the quantity L minus F sub E minus F sub O, all divided by F sub O. How has it changed? Well, notice that this is minus the quantity L minus F sub E over F sub O. The only thing that changes, you will subtract also the focal length of the objective. Now let's see how that changes the overall magnification of the objective lens. So this would be minus 20 minus 2 minus 5, all divided by 5. So this becomes equal to minus 13 over 5, which is equal to minus 2.6. So there you go. There's your new magnification of the objective lens. Rather than the minus 3.6, it's actually minus 2.6. So the first value we got was kind of an ideal value by simply saying, oh, we're going to put the object where the focal point is of the objective lens. But in essence, we actually put it a little bit further in front, which makes this image a little bit smaller, and the magnification is not quite as large for a microscope. But anyway, that's how you find the magnification of a microscope. And just again, to simplify things a little bit, the magnification is always the product of the two magnifications of the two lenses. The second lens is simply a magnifying glass, so we usually use relaxed vision or strained vision. That's very straightforward. Excuse me. For the first lens, we simply use the magnification equals minus S prime over S. S prime is going to always be equal to this. S will be equal to this if we kind of simplify things, but if we complicate things a little bit more by putting the object at the correct place, then it changes just a little bit, and instead of using this for the magnification, we add another minus F sub O in the numerator here to get the absolute correct magnification of a magnifying glass. And that's how you do that.